Hello everyone, welcome to another video. This video will be about the scope of physics. So this clip is focused on different scales and the ways we can compare them. Sometimes in physics we actually complicate things in order to simplify them later. That may sound strange, but it's a core virtue of physics. Mathematics can look more abstract at first, but it makes patterns more beautiful and explanations more clear. The first idea I want to talk about is logarithmic scales. So most of us in school, we're taught to think with linear or Cartesian scales, right? Where each axis we're changing by 1, 2, 3, 4, right? Each axis changes linearly. And that's what we're used to, and it works well for everyday problems. But when it comes to trying to compare things that are vastly different in size, linear scales break down. The distances are simply too large to put on the same graph. This is where logarithmic or log scales become essential. On a log scale, each step is a power of 10, not just one unit. So this could be 1, 10, 100, 1000, and then I'm just going to use scientific notation: 10 to the 4, 10 to the 5, 10 to the 6, 10 to the 7. Here's 10 to the 12, kind of skipped a few. And the same thing with this axis. Now you do have graphs where the y-axis is logarithmic and the x-axis is linear, but so I guess I'll just do that in this case. But anyway, sometimes the x-axis is just a label, right? But this allows us to place extremely large and extremely small things side by side. Imagine trying to graph the size of this room. The diameter of the Earth is on the order of 10 to the 7 meters. So the Earth can be here. The solar system, or the sun, is about 10 to the 9 meters. The solar system is about 10 to the 12 meters. Right? So because we have this log scale, it actually lets us compress the vastness of the universe into something we can see and study. That's why they are critical when comparing different orders of magnitude. Another place we see log scales is in technology. Think of computer power. The number of transistors on a chip has been doubling every 2 years, as we mentioned in the previous video. That's an exponential growth, right? If you try to graph exponential growth on a linear scale, it shoots up like a rocket and becomes unreadable, right? So it looks like this. But if we plot this exponential growth on the log scale, it actually looks like a straight line. That's because logarithms are inverse of exponents. The log scales are the best way to track exponential change. They turn complexity into clarity. So logarithms is the first topic I wanted to cover in this video. But the second idea that I want to talk about is ratios. Ratios are everywhere in physics. You know, a ratio is just one thing divided by another. It tells us how two quantities compare. For example, speed is the ratio of distance to time. Density is the ratio of mass to volume. Right? Ratios are powerful because they strip away units and reveal relationships. They let us compare things that might otherwise seem unrelated. So if I write speed is distance over time, and density is equal to mass over volume. So we can see that speed is just a ratio between distance and time, and density is this ratio between mass and volume. And ratios are everywhere in physics. I could have wrote down hundreds of equations. Anytime you have something divided by something, that is essentially a ratio. Although sometimes you can write ratios like this, like 1 to 2, 1 to 3. So here's a fun hook. Ratios also show up in everyday life. Think about video games. Your kill to death ratio, your score per minute, your level compared to playtime, or social media. Likes to followers, shares to views, comments to posts. These are all ratios, and they tell you something beyond the raw numbers. Physics works the same way. Ratios reveal patterns that the raw data just simply can't. So whether you're comparing galaxies, atoms, or even your favorite online stats, ratios help us find meaning. That's why they are one of the most important tools of all of science. So a quick recap. Today we learned about logarithmic scales. We saw that they let us compare things that are unimaginably big to things that are unimaginably small. They also let us graph exponential growth in a way that makes sense. We also talked about ratios. Ratios simplify comparisons and reveal hidden relationships. From physics equations to social media stats to video games and plenty more, ratios are everywhere. They help us make sense of the world across all the scales. So whenever you see a number that seems too big or too small to handle, remember, a log scale or a simple ratio can reveal the bigger picture.